Alright, today my partners and I will be reviewing the paper The Vulnerabilities of UAVs to Cyber Attacks and an Approach to Risk Assessment. This paper is written by Kim Hartmann and Christian Stedup of the Otto von Gunnrich University in Germany. I will be covering the introduction and some UAV basics. My partner Ralph will be going over some recent attacks and some proactive risk assessments. And finally, Richard will be covering the results of some experiments with an AR drone, a Reaper drone, and the Sentinel drone, and finally he'll be finishing up with some conclusions. Alright. As the US military becomes more computerized, it becomes more vulnerable to cyber attacks. From 2008 to 2012, the military has more than doubled its funding for drones and UAVs to $4.2 billion a year. Drones are currently used for a variety of tasks, ranging from reconnaissance to transport and even armed attacks on assailants. UAVs are reliable, automated, and autonomous. They are easy to use and require minimal training to get new pilots up to speed. However, they are considered vulnerable due to the number of different systems that are used to keep drones in the air. Drones have several different systems: avionics, GPS, communications, and onboard computer systems. Every one of these computer systems is a new attack vector that hackers can use to exploit them. Right, next we're going to be covering some UAV basics. UAVs, unmanned aerial vehicles, are complex technical systems. The number of systems leaves them vulnerable to various cyber attacks. Figure 1 here on the right shows the basic components of a UAV that is incorporated into use. We'll be covering more of these in detail on the next slide. The UAV components are composed of the base system, the sensor system, the avionics system, communications, ground control operators, weapons, and autonomous control. The UAV base system allows intercommunication between the components of a UAV. This is like the operating system. It combines the hardware and the software together. Next, we have the UAV sensor system, which consists of sensor equipment that is used to observe the drone's surroundings. Sensors such as camera, GPS, radar, LiDAR, hypersonic sensors. These allow the drone to observe its environment around it and eventually interact with it. Next, we have the UAV avionics system. Avionics is responsible for converting commands into flight control. The avionics is responsible for the rudder, aileron, and elevator of a drone, as well as the motor and throttle control. These are the physical parts of a drone that are used for flight control. Next, we have the UAV communications. Almost all UAVs are wireless, and they're required to relay their information back to the ground operators. Most UAVs civilian UAVs use 2.4 gigahertz, and military UAVs use different frequencies, which are of course classified. Next, we have the ground control operators. These are the personnel on the ground that observe, command directly, or give orders to the drone. They review the sensor information as well as different environmental controls that would affect the drone. Then we have the weapon system. These control any missiles or guns or bombs the drone may have on it. And finally, we have the autonomous control. These computers allow the drone to fly based on external inputs from sensors. They allow it to be completely anonymous, so it doesn't require constant user input. This is also useful if the drone loses communications. It will be able to fly itself or navigate waypoints for a predetermined period of time. Every one of these components is vulnerable to cyber attack in some way or another. So that's why it's important that we clarify each one, because we're going to be going into how they are vulnerable later.
This paper reviews a couple of prominent vulnerabilities that UAVs have been shown to have in the past, as well as a couple of instances where those vulnerabilities have been leveraged by attackers. One of the most famous instances of an attack against a military UAV in particular was that of the RQ-170 Sentinel by Iranian forces, where they were actually able to safely land one of the UAVs in question in order to compromise it. There were a couple of different theories about how they were able to accomplish this. The most prominent theory was that they'd launched a GPS spoofing attack against the UAV sensor systems, which essentially has a GPS signal sent from a local node that is stronger than the satellite-based GPS signal. So essentially, it overrides the satellite GPS signal, making the UAV believe that it's in a position that it actually isn't, and then giving the Iranian forces the ability to land said UAV wherever they see fit to do so. That was a really sophisticated attack, but it wasn't necessarily an impossible one to pull off. It was just uncertain whether or not the Iranian forces actually had the sophistication and skills in order to make that happen. The other theory behind the RQ-170 Sentinel attack was that there was a technical malfunction that just made the UAV land in Iranian territory, and the Iranians just picked it up from there. In this particular instance, there was a big debate as to what should happen to a UAV once it has been compromised, or once it is in once a severe fault has happened in its mission. A lot of people are saying that it should just self-destruct, but in this particular instance, due to some technical malfunction, it wasn't able to do so. And so the confidential information that it had on it, confidential information like force movement, mission-specific information, as well as just the technology in general, was indeed compromised. Beyond that, there are a couple of different other ways that UAVs can be compromised. One of the big ones is attacking the GCS, and you can do this through a wide range of viruses, such as keyloggers. Those sorts of threats can do anything from compromise just the security and confidentiality of a UAV to actually allowing the attackers to control said UAV. Taking into consideration all of the information we've seen up until this point, this paper offers up the proactive risk assessment scheme as a competent strategy for figuring out the risk to any part of a UAV on a given mission. This particular scheme is based highly on the components of a UAV and the risk involved with those particular systems. It's probability based, meaning that a very susceptible system that which we can assume will have a higher probability of attack is given a higher score. So in this particular scheme, a 0 means something is absolutely not acceptable, and a 1 means something is highly susceptible to an attack. So anything in between there is what we're going to be gauging off of. Of course, the higher number being the more susceptible to attack it is. Particularly, this is looking at the CIA triad of a UAV, so the confidentiality, integrity, and availability of that UAV. And it takes a look at that in reference to the systems of the UAV. It's multidimensional, meaning that things can be weighed differently depending on the risk associated with them in a given mission. The proactive risk assessment scheme takes into consideration various factors associated with UAVs. I'll go over a few of them now with you. The first big factor that is taken into consideration is the environment that a UAV is going to be placed in. The environment influences everything that has to do with the UAV, from its avionics to its communications to its sensors to basically anything having to do with its mission. Now, from that definition, you might think that environment would have to do with the physical aspect around a UAV, but that's not necessarily the case. I mean, of course, the physical location of the UAV is important when you take into consideration the landscape, air humidity, weather, things like that. But environment also goes into the idea of the political environment that the UAV is going to be into. Essentially, if the UAV is flying in clear weather through friendly territory, it's going to have a different risk assessment than if it's flying through clear weather in enemy territory or in a war setting. Environment covers this. Next on the list is the communication link for the UAV. Now, this is important because different types of communication between the UAV and the ground control center are more or less susceptible, depending on a lot of different situations. So, for instance, here in this paper, they talk about the Tactical Common Data Link, which is an encryption, or rather, an encrypted form of communication used by the U.S. military. It operates at a really high level, like 15.15 gigahertz to 15.35 gigahertz. Uplink, and 14.40 gigahertz to 14.85 gigahertz downlink. This means that while it's really difficult to eavesdrop on this particular channel, it might be more susceptible to physical issues like weather. It's really kind of spotty with humidity, for instance. Another thing is just the C-band, which is communications from 4 gigahertz to 8 gigahertz. This is also kind of difficult to eavesdrop on, but there are a lot more applications that use it, like satellite communication, certain Wi-Fi communications. But it can still be listened in on. The last form of communication that they go over in this paper is Wi-Fi, and they go over specifically Wi-Fi A, B, G, and N. Now, of the Wi-Fi standards, they say that A is kind of one of the more susceptible to eavesdropping, and basically it really is hard to maintain without somebody being able to listen in on it. Whereas N is a little more secure, and B and G kind of fall in between those two. And another big important thing to consider when it comes to the security of UAVs is their sensors. Different sensors can be attacked in different ways, and that could affect the mission of the UAV. For instance, if GPS sensors are attacked, like in the RQ-170 Sentinel attack, it could pose a significant risk not just to the mission but to the UAV itself. Other communication signals can be jammed. Values that are important for the sensors to keep can drift, and that happens naturally. But if it happens in such a way that it's not dealt with in a safe manner, the UAV could be compromised. And not just by an attacker, it could be compromised just through a technical fault. Continuing our discussion of areas of assessment, we'll move on to data storage. This is really important in a UAV because how data is stored and where it's stored can really change the risk value associated with it. For instance, you have volatile data, rather volatile storage, and volatile storage can be risky in that unless there are really good coping strategies for the volatile storage, things can be overwritten that should not be, and that can compromise the integrity of the data. But also associated with that is encryption. Now, no matter what kind of storage you put data in, if it's properly encrypted, you're going to really improve the confidentiality score that it would have. Unencrypted data, no matter where it's stored, can be compromised by an attacker or some other nefarious actor. Still, data encryption doesn't mean that that data can't be overwritten, so the integrity of the data doesn't really get affected by whether or not it's encrypted or not. So in this paper they looked at a lot of different storage mechanisms. They had magnetic tapes, hard drives, solid-state storage, and temporary storage through RAM in particular. But any storage method that they used, if it were properly encrypted and had proper signatures on it, while no matter what kind of value it would have had otherwise, for instance, hard drive-based storage has integrity and confidentiality value of 0.9, which is really high, which is really susceptible to attack. If it's properly encrypted, that value goes straight down to 0 because an attacker just can't get into it. And the final area of assessment that they looked at were fault handling mechanisms. Now, these are pretty important. Issues are going to come up in any real-world mission, And any UAV that is operating at military level needs to be able to handle situations uh, by either by getting information from the ground control station, or more likely making autonomous decisions on its own. Now, these fail-safes typically fall, or rather, these faults can typically fall under two categories. Either they're transient faults or they're permanent faults. A transient fault is going to be some sort of external temporary disturbance, like lack of communication or cloud cover messing with avionics information, things like that. A permanent fault is going to have something wrong with hardware, like you're going to have some damage, or you're going to have some part of the internal computational system compromised in some way. Now, these particular fault handling mechanisms are tricky because the only way to really figure out the risk assessment for them, or rather to assess the risk for them, is to go through each possible fault with a fine-tooth comb and see what you have available to deal with that fault. A lot of the different strategies that are available, pretty much they fall under four categories, especially if it's a mission-critical fault. You'll have hover, land, automatic return, and self-destruct. And I feel like those are pretty self-explanatory. And all of those have different fault levels on them, or different risk assessment levels to them. For instance, the self-destruct strategy has a very, very low risk assessment, because while, of course, the availability of the UAV is completely shot, so you're going to have that at pretty much a straight 1, the integrity of the information and the confidentiality of the information on the UAV is going to be perfectly safe. Whereas the strategy land is going to just be really, really risky. It's going to have the integrity, confidentiality, and availability scores all at 1, because you don't know where it's landing. So the enemy might be able to get it and compromise the information on it.
My name is Richard Estape. I'm going to be presenting the rest of the slides. First, I'm going to be presenting the results of the paper. The researchers applied their schemes to 3 modern UAVs, the AR drone, the MQ-9 Reaper, and the RQ-170 Sentinel. Here you can see the result table for the AR drone. Some of the things that the researchers were able to observe were the used INS is accompanied by an optical flow measurement of the ground to track the position. This represents a checked mandatory sensor. And then another thing that they were able to show is that the low altitude distance sensor can be used to manipulate the flight height of the drone, which if this goes unchecked, it can be a problem. And the cameras never overlap, which prohibits image cross-validation. The next drone that they applied their scheme to was the MQ-9 Reaper. This is a remotely controlled UAV. It is a successor to the MQ-1 Predator. It uses the TCDL satellite communication system as well as the direct LOS C-band communication. The control of this drone or UAV is done by GCS. The equipment on it consists of several cameras, which all together are used to create the multispectral targeting system that the drone has. These cameras detect infrared, daylight, and intensive light. The data is automatically processed and fused by the drone systems, and the navigational sensors are INS and GPS. The MQ-9 Reaper contains digital storage for video data, unlike the last drone that didn't have any storage. The encryption and the signature mechanisms are unknown. Seeing that this drone is used primarily as military use, there's not too much public information that the researchers could gather. And the next slide shows the data that they were able to collect. Here you can see the table that corresponds to the MQ-9 Reaper. The communication systems on the drone, it uses two independent links, and they're both encrypted and signed. The data storage, however, the encryption and signature methods are unknown for that, but the researchers think that worst case scenario, there is no encryption or signature methods. This could be an issue for the drone, leaving some of the data vulnerable, some of the video recordings vulnerable to attacks or hacks. And then in case of an accident, the remote pilot must cope with the faults manually, and also the self-destruct mechanism is activated manually. This can lead to uncontrolled landings or flights, and it causes an issue with availability, integrity, and confidentiality of the system. The next drone that they tested their scheme on was the RQ-170 Sentinel, and unlike the other two, there is very little public data available for this UAV, and this has to do with the fact that there is an investigation going on that the Iranians claim to have attacked the RQ-170. The sensory equipment on the UAV consists of infrared and daylight cameras, as well as GPS and INS. The equipment is very similar to the MQ-9 Reaper, and the risk assessment that the researchers use is heavily based on the same equipment that's on the MQ-9 Reaper. So the data storage is non-volatile, same as the other one, and the encryption and signature mechanisms are unknown. The communication link and the fault handling mechanisms are also unknown. The scheme that the researchers used was the first attempt to formalize the risk assessment of a drone. The current risk assessments are lacking. They're far behind where they should be. And the risk assessment of the UAVs was complex, and the task consisting of finding the vulnerabilities was heavily based on the task or mission that the drones were doing. And the components of each drone were tested based on the technology and the known vulnerabilities. And the scheme that the researchers used were applied to two drones, the AR drone and the MQ-9 Reaper. The other drone, they were only able to assume some of the components because it had very limited, that drone has very limited public data due to the investigation that I talked about in the previous slide. The calculated values gave the researchers an indication of how susceptible the UAVs are to attacks. These attacks usually influence availability, integrity, and confidentiality. It was shown that the risk assessment of UAVs is highly dependent on the assignment and the mission that the drone is used for. The described method is a first approach to a general scheme for the risk assessment of UAVs. The analysis and the assessment of each of the components describes an individual area of research. As time goes on, as each individual component is researched more and more, there will be better schemes and better methods of coming up with how vulnerable these drones can be. The paper serves as a basic but crucial introduction to the risk assessment of UAVs. So hopefully these researchers were able to come up with a blueprint as to how to assess these drones and their vulnerabilities, so that as newer drones are made, they can be examined and tested for vulnerabilities to make them more secure against attacks.